Hello students. So, in the previous class we started with Gauss divergence theorem, and we also looked into the statement of Gauss divergence theorem and how we can convert a surface integral into a volume integral, and then a volume integral back into the surface integral. So, whichever is given, if in your question if you are asked to evaluate the other one, you can use the Gauss divergence theorem. And since we have only 2 more lectures left, today we will start with one example on Gauss divergence theorem, and then we move to our final theorem in vector calculus, which is basically Stoke's theorem. And unfortunately, we do not have any more lectures left. So, we may not be able to practice examples from the integral calculus section or even from the introduction of the vector calculus part. But we will try to solve at least 2 or 3 examples on Stoke's theorem, just to make the concepts clear. So, today we will start with one example on Gauss divergence theorem. So, in the statement from the Gauss divergence theorem, you remember that you can write if f is any vector function, then you can write a volume integral over v divergence of let us say our vector function is f. Then in that case I can write divergence of f dv equals to surface integral, and here you have curl of f dot n ds. So, this is basically our I am sorry. So, this one is just f dot n ds. So, this is basically our Gauss divergence theorem, and with the help of Gauss divergence theorem, you can be able to convert, or if you are given to evaluate a surface integral, you can just convert it into a volume integral, and the things will become very straightforward. So, we will solve one example based on this Gauss divergence theorem. So, the first example is for today. So, the first example is let us say by converting the surface integral into a volume integral evaluate surface integral over S x cube dy dz plus y cube dz dx plus z cube dx dy, where S is the surface of x square plus y square plus z square equals to 1. So, this is basically our sphere, and we have to convert the surface integral, which is to be evaluated on the surface of this sphere into a volume integral, and then we have to calculate the value of this surface integral. So, we know that from Gauss divergence theorem, we know that so we have learnt this formula. So, there are like 2 or 3 expressions for Gauss divergence theorem, and one of them is this one, another one is with dx dy, dy dz and dz dx form. So, we are going to write that form here. So, by divergence theorem we know that surface integral over S f1 dy dz plus f2 dz dx plus f3 dx dy equals to volume integral over V. We will have f1, we have del f1 del x. So, this is a bit bigger bracket, del f2 by del y, and then we have del f3 by del z, and then here we have dv. So, which is basically dx dy dz. So, this is the required how to say form in terms of Cartesian coordinates like x, y and z. So, now we can compare. So, you see this surface integral here and this surface integral here. If we compare these 2 forms, then in that case our f1 is x cube, f2 is y cube and f3 is z cube, right. So, we have where V is the so here V is the volume enclosed by the surface S. So, we have f 1 x y z as x cube, f 2 x y z as y cube, and f 3 x y z as z cube. Since f is a function of x only, f 2 is a function of y only, and f 3 is a function of z only, it makes our life a lot easier, because it may happen that here f 1 could be a product of x y z and their power and things like that. So, then it would have become a little bit complicated, but since here everything is just like a function of one variable only, then this is a fairly simple example to do. So, now by the divergence theorem, let me name this equation as 1. So, from equation 1, if we convert this surface integral, into a volume integral, then it will take this form like in equation 1, and in equation 1 V is the volume enclosed by this sphere S, which is given here, and we have to evaluate del f 1 by del x. So, if I do the partial derivative, then this will be del f 1 by del x 3 x square, del f 2 by del y 3 y square, and del f 3 by del z 3 z square. All right. So, let us substitute all these values here. So, from 1, and let me call this equation as 2. So, this is as 2. So, from 1 and 2 we have volume integral over V del f 1 by del x square. So, basically 3 x square plus y square plus z square dx dy dz. Now, this is basically volume integral, and if we substitute this as x square plus y square plus z square as here as 1. So, then in that case this will become 1 dx dy dz, and this is volume integral. So, 1 and then dx dy dz is basically dv. So, that is the volume element. So, I can write it as dv, all right, and this means that we are basically doing or calculating the volume of that sphere, right. So, if your vector function is 1, like in this case, and I mean not vector function. So, if your function overall is 1 in a way, then in that case here this means that you are actually doing a volume or calculating the volume of the given surface. So, that is what this means, and here in our case the given surface is a sphere of unit radius. So, in that case we can write 4 by 3, or what we can do is instead of substituting, there is another method which we can follow. So, what we can do, instead of substituting this one, I can substitute, just to make things a little bit more clear, I can substitute x equals to r cos theta cos phi, y equals to r sin theta sin phi, and r cos theta sin phi, and z equals to r sin theta. Then in that case this will be x square plus y square. So, cos square theta will get out, and then this will be cos square phi plus sin square phi, and then that will be 1, and then it will be r square sin square theta. Yes. So, this is correct. So, we substitute x equals to r cos theta cos phi, y equals to r cos theta sin phi, and z equals to r sin theta. So, if I substitute all these values here, then in that case this will be r square times r square sin theta, and then we will have dr d theta d phi, all right. So, now for this V, what we can do is we can write the range for r. So, r is basically varying from 0 to 1, theta is varying from 0 to pi, and phi is varying from 0 to 2 pi. And if we evaluate this integral, then this will be r to the power 4 sin theta dr d theta and d phi. So, we can integrate because they are not in a way involving theta and r together. So, we can integrate with respect to r for the integral with respect to r, and we can integrate for theta for the integral with respect to theta. So, that means this will reduce to integral r running from 0 to 1, integral theta running from 0 to 2 pi. So, first we will integrate with respect to phi. So, this will be theta. So, this will be integral from 0 to 2 pi d phi, and here we will have dr d theta. So, this will give us 2 pi. So, this is 3 times 2 pi, and then we integrate sin theta. So, it will be cos theta, and theta is from 0 to 2 pi. So, then we will have cos pi as minus 1. So, this will give us a 2, and when we integrate r to the power 4, then this will give us 1 by 5. So, ultimately it will be 12 by 5 pi. So, you see initially we had a very how to say complicated expression where it is not that much complicated, but still we had to calculate this surface integral. So, in the question itself it says that convert this surface integral into a volume integral. So, if we are asked to convert this surface integral into a volume integral, we just have to use this divergence theorem, and in that divergence theorem if you compare, then this is basically our f 1, this is basically f 2, and this is basically f 3. And on the right hand side of that divergence theorem, we had to calculate the partial derivatives. So, we calculated the partial derivatives, we substituted these partial derivatives here, and then we are just substituting, taking the help of spherical polar coordinate system. So, we substitute r equals to cos theta cos phi, y equals x equals to r cos theta cos phi, y equals to r cos theta sin phi, and z equals to r sin theta. So, the volume element will be dr d theta d phi multiplied by r sin theta, and then we have here r square basically. So, so this is our basically volume element, and that is the function what we are getting from this x square plus y square plus z square. So, altogether this is r to the power 4, this is sin theta dr d theta d phi, and the limit for r is 0 to 1, for theta is 0 to pi, and phi is 0 to 2 pi. Then when you integrate, you obtain this integral, the value of this surface integral. So, that is how we use the Gauss divergence theorem. So, whenever you are given a surface integral, you can use Gauss divergence theorem to convert it into a volume integral, and it will become very easy, because when you are evaluating surface integral, in some cases you may have a parallelepiped or cube or a cube, and then in that case you have to do the surface integral on every surface. However, if you convert that surface integral into a volume integral, then the life will become much easier. Then in that case we just have to get the limits for x, y and z, and do that, calculate that divergence, and hopefully the whole thing will become very easy. So, this is one of the examples motivated from Gauss divergence theorem, and now we move to our final theorem, which is basically Stokes theorem. So, I am going to write the statement first. So, Stokes theorem. So, let me have a look at the statement in my lecture note. So, the Stokes theorem says, let S be a piecewise smooth open surface bounded by by a piecewise simple closed curve C, and let f x y z be a continuous vector function which has continuous first order partial derivatives. In a region of space which contains S in its interior, then line integral f dot dr equals to surface integral curl of f dot n ds, or we can write it as where n is a unit outward drawn normal. All right. So, this is the required statement, and of course, so if you are walking along the curve C, then your surface S must lie on the left hand side. So, that is how we choose the curve C, that the orientation is always in the anti-clockwise direction. So, that is the property of this curve C, and n is outward drawn normal. So, if you are walking in the anti-clockwise direction, then your surface will always lie on the left. That is how we mean by closed, that is what we mean by this piecewise smooth bounded by a simple closed curve, piecewise simple closed curve C. And n is actually the outward drawn normal on the surface S, and then in that case you can write the line integral f dot dr as surface integral curl of f dot n ds. So, this is also a very important theorem in vector calculus and also in applied several other branches of applied mathematics, where we take help of this theorem. So, for example, in partial differential equations or even in fluid mechanics, these theorems have a very wide application. So, this is the required statement, and we can also write this theorem in a Cartesian form. So, I have it in my lecture notes here. So, if I write it as a Cartesian form, then in that case we can write it as alternatively, or a different form basically. So, alternative or a different form, So, basically let f is a given vector function which has 3 components, f 1 I, f 2 j and f 3 k, and let n the outward drawn normal, makes angle alpha, beta and gamma with positive directions of x, y and z axes. Then we can write our normal n. As cos alpha I plus cos beta j and cos gamma k. And we know that curl of f, so curl of f, if f has 3 components, then curl of f is basically a cross product which can be determined by that determinant I j k f del x del y del z, and then f 1 f 2 f 3, and then we calculate the determinant. So, we basically take a dot product with this normal n which is given here. So, on the left hand side basically we will have line integral. So, therefore, f 1 I plus f 2 j plus f 3 k dot product with dr. Dr is basically dx I plus dy j plus dz k equals to surface integral. So, here we have curl of f. So, if we calculate the curl of f, or let us just write curl of f dot n. So, n is cos alpha I cos beta j plus cos gamma k. So, now we can calculate the curl of f easily, and then we take the dot product. Here also we take the dot product, and therefore, the whole thing will reduce to and here it will be surface integral del f 3 del y minus del f 2 del z times cos alpha plus del f 1 by del z minus del f 3 by del x cos beta plus del f 2 by del x minus del f 1 by del y cos gamma d of s. So, this is the required form of Gauss divergence Stokes theorem in the Cartesian form. So, Green's theorem or Gauss divergence theorem, Stokes theorem also has very wide application in vector calculus, and we will practice a few examples motivated from Stokes theorem, and then we will probably close this topic. So, let me just try to find out. Okay. So, here I have some examples. So, example 1, I guess. So, first example is prove that line integral of r dot dr equals to 0. So, we have to show that so that line integral of this r is our given vector function in this case. So, f is basically r, and line integral over this curve C, where C is again any piecewise smooth curve, closed curve of course, dot dr equals to 0. So, we can write this as surface integral curl of r dot n ds. So, dot n is basically the unit outward drawn normal, and we have to calculate the curl of r, right. So, curl of r, if you calculate, then you will be able to see that this is 0, because r is x I plus y j plus z k, and if you calculate curl of r, then this will be 0. So, surface integral over S 0 dot n ds is equals to basically 0. So, this is how we use the Stokes theorem. Next, we can apply we can show that a similar type of result. So, show that. So, there are several show that type of problems which you can also solve with the help of Stokes theorem. So, show that line integral over the curve C phi gradient of phi dot dr equals to 0. So, our given function f is basically phi times gradient of phi. So, here we can have surface integral phi line integral c and gradient of phi dot dr equals to surface integral of curl of phi grad phi dot n ds. So, now we have to calculate curl of phi times gradient of phi. So, if we do that, then in that case using the formula from vector calculus, this can be written as phi times curl of gradient of phi plus gradient of phi curled with gradient of phi cross product with gradient of phi dot n ds. So, now this is gradient of phi cross product with gradient of phi. So, this is basically 0 because a cross a is 0 and phi times curl of gradient of phi is also 0. So, this is also 0 and this is 0 by definition. So, ultimately we have this as 0, this as 0. So, the integrand is 0 and therefore, 0 vector dot n is again 0. So, that means this whole thing will reduce to 0 dot ds. So, because this is 0 vector, this is 0 vector. So, 0 vector dot with n cap is a 0 scalar and then we integrate over surface integral s, let us say. So, this is ultimately 0. So, you see we did not have to go through any complicated calculation or something, we just had to use Stoke's theorem. That means you can convert your line integral into a surface integral and then the rest of the simplification is pretty much straightforward. So, these were the two proof that examples that we solved today, but in our next class we will consider at least 1 or 2 examples motivated from the Stoke's theorem, where we might need to verify the Stoke's theorem, and we will start such examples in our next class. So, I thank you for your attention today and I will see you in your next class.